This is the screencast for section 3.1, example 5. I didn't really like example 5, so I'm not doing example 5. Instead, we're just going to do the now try problem. We're going to use some data and look at how you find a derivative with data points. We've got a downhill skier here, number 29, and table 3.3, that's what this is. So these data points were originally given, and they give the approximate distance traveled by the downhill skier after t seconds, between 0 and 10 seconds. We're going to use the method of example 5 that I don't like. I like the method, but I didn't like example 5. To sketch a graph of the derivative and then answer the following questions. So first of all, I wanted to know what the original function looked like. So this is f of x, the skier's distance. So down here is time, and on the side here would be feet. I guess time would be specifically in seconds. So for f of x, I put L1 and L2 to be time in seconds and distance traveled, and I use those exact values. So the derivative, to sketch that, I need to find the slope of each tangent line. Well, the problem is I don't have an equation. Yeah, I could use my calculator and come up with maybe a quadratic regression or something like that, but we have a method in calculus to find or estimate the derivative using data points. What we'll do is we will take, we've got points, so we're going to use them to find slope. So for example, we will take this point right here and this point right here, calculate the slope, but then that slope won't be tangent to either one of those data points, because which one do you pick? Instead, it'll be tangent to a point right in the middle. However, for f prime of x, I used in between the x values. See, between 0 and 1 was 0.5. Between 1 and 2 was 1.5. Then for the y values of the derivatives, I just calculated the slope using data points. So for example, if I zoom in, it's like I have these two data points, 4, 53.2 and 5, 83.2. I have these two data points. Well, I find the slope connecting those two data points, and that's change in y over change in x, so 30 over 1. But I'm not going to make that the derivative at 4 or the derivative at 5, but the derivative right in the middle at 4.5. So that's where you get the point 4.5, 30. So part A asks, what does the derivative represent? Well, I can tell you that the x values are going to stay the same, and that's still going to be time in seconds. The y values, though, are going to represent the slope. So the slope would be change in y over change in x, so change in distance over change in time, so that's feet per second. So what does the derivative represent? It represents the velocity of the skier in feet per second at any given time in seconds. So if I want to know the skier's velocity at 8.5 seconds, it would have been 56.6 feet per second. The velocity at 2.5 seconds would have been 16.6 feet per second. B, in what units would the derivative be measured? Oh, look at that. We already thought ahead of ourselves. That's feet per second. Again, that came from the change in y over change in x, and the change in y is in feet and the change in x is in seconds, so it's feet per second. Part C, can you guess an equation of the derivative by considering its graph? Well, let's see. Its graph looks pretty linear to me, so I plotted the time in seconds into L3 and then the slopes into L4 to get this data graph. I kept the window the same just to give it some perspective. So, can I guess the equation of the derivative? It's going to be linear. I'm going to say it's going to be y equals about, let's see, if I were going to pick a slope, maybe beginning to end. Well, I don't know, I can just pick any 2 points as an approximate slope of this line and go from there, and I think it's going to be maybe about 6.3 t. Your book says it's about y equals 6.65 t, But the idea behind this is it's approximate. We don't know because each of these little data points has a slightly different slope than the other. So depending on what point you choose to approximate the slope, it might vary a little bit. So I'm going to definitely put down here that the equation will be approximately y equals 6.3t. Now I know the y-intercept is 0 because at time 0 the skier wasn't moving at all, so that is pretty definite.